let's practice with two-slit interference. So we've got a problem in which we're shining two colors of light at this double slit. So one color we know, orange light, so here are its wavefronts, okay, and they are separated by a distance I'll call lambda O for orange. And there's another color of light in here, and I don't know how big its wavelength is. I'm just going to maybe guess that it's smaller, so I'm going to draw the wavefronts as smaller, okay, but they're both traveling, but this distance here is an unknown wavelength I'll just leave as just lambda, okay, and I'm trying to find out what that is. Now the way I'm going to investigate it is as these two colors of light hit these slits, they're gonna fall onto a screen, and I'm going to see an interference pattern. There's going to be bright spots for one color and bright spots for another color. Now what I know, and I'm going to draw a little more carefully horizontally here, if I'm looking at this, so we've got a bunch of bright spots on here. If I'm looking on this, I'm going to just look to one side. Okay, I have the bright spot of the orange. They will have a central maximum right at 0, and that's the 0th order. That's at the no displacement between the two, or no difference in path between the two slits. Okay, and then for the first one, that's where the two paths are one wavelength different. It's the first order, and then I'll have the second order one and third order one. I'm doing my absolute best to draw these at equal intervals. Okay, so this would be the first order, the second order, and the third order. Okay, which implies that this is the path from the two slits or to this spot on the screen is one wavelength different, two wavelengths different, three wavelengths different. So this is for the orange. Okay, I'm going to use O for that one. Now what we see is that the other color has its fourth order maximum overlapping with the third order maximum for the orange. So it must have narrower peaks. I'm going to draw it like this. And they must be closer together. So that the fourth order overlaps with the third order. So this is 0 here. Right here is 1. This one's 2. This one's 3. And that one is 4. So these other ones don't overlap, but this fourth one overlaps with the third one. So this is our unknown wavelength. I don't know what it is. And we want to find out what that wavelength is with this information. Knowing, okay, I know that the wavelength for the orange is 600 nanometers. Okay, and that's all I'm given. Okay, now the rest of the information I have to pull from this. So let's see if we can find the unknown wavelength. Okay, so what information do I have? Well, because I don't know the distance between the slits, I don't know how far the screen is from the slits, but let's see if I need that. Okay, so using our two-slit interference equation, say that D times Y sub M over the length is equal to M lambda. Okay, so this Y sub M is the distance from here to, that would be Y sub 1. Okay, that would be what from here to here is Y sub 2, here from the origin to here is Y sub 3. So this is our relationship to the mth, the distance to the mth bright spot for a path difference equal to M times lambda. Okay, so we know something about this wavelength, and we also know that third order maximum for orange is the same place as the fourth order maximum for the unknown. So let's go and write those two out. We have Y sub 3 for the orange. Okay, multiply the L up and divide the D down would be M, which is 3, which I should just put 3 there, but we'll just do M sub 3 to indicate that's a 3. And then times L times lambda orange divided by D. Now L and D are not specific to orange. They're specific to the apparatus, how far the screen is in the slits. That's the same for the other color of light. The only thing that's different is this is a 3, and that's 600 nanometers. So I can write Y of the fourth order maximum for this unknown wavelength is going to be, just to be consistent here, again I should have just written a 3 there, M sub 4, or the fourth order, times L times this unknown wavelength divided by D. And the thing I know is that those are equal. So solving for that, I'm going to go and plug in my 3 now. I have 3L lambda 0 over D equals 4L lambda, my unknown one, over D. And now the things that are the same are the distance to the screen, the slit widths, and so this lambda, unknown lambda, is now equal to, I can divide the 4 down, 3/4 times lambda of orange. Okay, and since lambda of orange is 600, 3/4 of 600 is 450. So that's 450 nanometers. Okay. Now that makes sense because I know that the smaller the wavelength, the tighter the distribution is. These peaks get closer and closer to this central peak, but it's still visible light. That's in the bluish area, and so that makes sense to be an accurate value for this. And so I also did pick. Now this you wouldn't have known ahead of time, but I did pick the wavelength to look smaller here as it's coming in too, which does happen to match the final answer.